Okay. I think we can start. I'm very happy to be back with you after a week of absence, and I realize that it's hotter in Freiburg than it was in Rome last week. So yeah, it's more humid here actually. But anyway, okay. I learned a bit about optimal control and numerics from other people, and I will share a bit of this later with you. But what I want to share with you today is the leftover that is not yet in the script, but I'm in the process of uploading it or actually writing it, about differential dynamic programming. That is one method that is something that's not so much known among mathematicians. So also I asked there last week, no one knows about that method. But when you ask computer scientists or also robotics researchers, many of them know it, yeah? And they know it under slightly different names, but all of them know the name differential dynamic programming, and that's why I want to give this section this title. And it's, so to say, my own effort to merge the work from different communities that did not yet recognize that it's all the same, so to say. But anyway, okay. So this section is about differential dynamic programming, and it will be, I think, 8.9. And you will see that it's not something too complicated, but as I said, it's an algorithm that is popular, differential dynamic programming, because it's simple and efficient at the same time, DDP. And that's basically the name that you give to it, DDP, like differential dynamic programming. And maybe I should say that the work on dynamic programming, we just had that. It's a technology that is most often used in discrete state spaces of small dimension, a small finite number, right? That's where it really works well, like when you enumerate the locations which, like for shortest path problems in a street network in a city like Freiburg, it's relatively easy to enumerate, so to say, all crossings, because it's maybe a few thousand only, yeah? Once you would discretize a state space that's continuous and you discretize it in 20 dimensions, for example, just having 10 points in each direction, it's already 10 to the 40 different points, and you could not use dynamic programming as it is, right? So this is something that's known to everyone who knows about dynamic programming. And then there's this beauty of the linear quadratic regulator. That's like the only exception where you can do dynamic programming with a decent or medium or larger state dimensions. And still get a nice and accurate solution, which is actually running with a forward and a backward sweep like dynamic programming. And so the idea of differential dynamic programming is actually the same idea that we have in all Newton-type methods. And so it is, in fact, in disguise, a Newton-type optimization method. The idea is that you take a continuous time dynamic system, yeah? So something that is differentiable, has continuous state spaces, continuous control spaces. You simulate it along some trajectory. You linearize along this trajectory, and then you do a quadratic expansion of that trajectory, and then you are back at the LQR, so to say, and then you solve it with the Riccati recursion that we have discussed before. So that's the rough idea, and there's nothing new about that. But then there is a little change that's not exactly how we would do it when we would just do single shooting, because what I described was single shooting. And this little difference is, I need to write it down also on the blackboard, of course, but this little difference is that when in single shooting you apply the Newton step, then you would set all the controls at once to the new value that you computed. Yeah? So you compute a trajectory, you linearize, you have a quadratic problem, you get a step, and then you have a step in all the controls along the whole trajectory, and then you could go into that direction. In differential dynamic programming, you actually simulate every single step of your dynamic system using the linear quadratic feedback law from the linear quadratic regulator. So you linearize your nonlinear system, you simulate your nonlinear system forward. So that is basically the only difference to single shooting. So I will just explain this class of family. And what I will comprise is also some classes. So DDP, as I said, is like the original algorithm. That's something that's going back to Main 1966. It's a very old paper. Then there are some much more recent papers. There is one algorithm that is related. It's called SLQ. And there is also an algorithm ILQR. Yeah, so they, I think, all know about that. And this was Sideris, one person called Sideris. I forgot the exact year, but it was 2000 and X. And the same, Sideris and Bobrow. And the other was ILQR, and that was, I think, Todorov, or Lee and Todorov, I think. And that was Todorov 2000 and X as well. And in particular, this paper, I think, made this algorithm extremely popular again. Yeah? As we will see, I will give some details about these different algorithms during the explanation, but they are slightly different, but very related to each other and know about each other. And maybe I should just say, this is the only algorithm that we know already, even though it's not known under that name to us yet. So this would be single shooting with the Gauss-Newton Hessian. So we know about what we would do then, right? Gauss-Newton Hessian. So that's an algorithm we are all familiar with. And then also I should say and Riccati linear algebra. So it solves the QPs with Riccati. So this is like the only algorithm we already know. And the other two, they are slightly different. And this little difference I will explain when we come to the point. So maybe to start, I would just like to recall the optimal control problem that we want to solve. And that is the minimization of over all trajectories in X and U. X and U are now discrete time trajectories, and my objective is the sum of stage terms, maybe I make them depending on I, plus terminal cost X depending on N, so this classical thing. And I goes from 0 to N minus 1. So that's the unconstrained objective, and to be more general, I think I could give you also an index here. This doesn't make a big difference, but it could be time-varying functions. And then the only constraint is that our initial value, x0, starts at some x0 bar, so like some initial value which is fixed, and then there are the system constraints. Xk plus 1 is equal to f of, sorry, I used an I now, right? I, ui, and that could also be time dependent, and I goes from 0 to n minus 1. So if you look at that, it's nothing familiar, nothing too fancy. It's just an unconstrained optimal control problem. And so for an unconstrained OCP, we know that we could linearize it along a trajectory, right? And if we linearize it along a trajectory, and this is partly a repetition what I do, yeah? So we linearize it. And in these things, we would linearize it at a feasible trajectory. And feasible for this case means only that that each following x is actually really given as a map, as this nonlinear map here. So at a feasible trajectory, x and u, you can linearize it. So basically, if you know the u, you can actually simulate the system forward, and then you can linearize it. And what you will get as a linearization is a linear quadratic problem that I can write in different spaces, but I think I maybe call this trajectory x0 bar, x bar and u bar. So I give 2 bars on top of this to distinguish it actually from the linearization point. Yeah. So this is a trajectory that satisfies. I mean, you choose the u bar, which is a whole trajectory, then you go through the system dynamics, and then you get the whole x and u trajectory. Clear? That's single shooting basically, or sequential approach. And then afterwards we will get a linear quadratic version of this whole thing, where, and now I should write it carefully, we would yet, and I don't care about the quadratic terms yet, or maybe I just give it another name. So we minimize over x and u again. A linear quadratic expansion I will discuss in a minute. So I call these L, maybe I give the upper or lower index. How do I do it? QP I at xi and ui. So these depend, of course, on the linearization and on the way of Hessian approximation and so on. So this is what this is quadratic terms plus a quadratic term which I call EQP. Yeah, so it's also quadratic of xn. And my constraints are now, okay, what are the constraints? And the constraints are that the initial value x0 should be equal to, I mean, feasible trajectory starting at x0 bar bar, right? So the initial point should really start at x0 bar bar, which is also, by the way, equal to x0 bar. So there is no difference between x0 bar bar because it's a feasible trajectory. This is now the linearization point. And xi plus 1. And here we should actually work with differences, no? But maybe I should do it this way. So we know that the difference between so this is now a linearization of that constraint at a feasible trajectory. And the linearization will actually mean that we have here a term ai, which is multiplied with xi minus xi bar. And here we have a bi, which is multiplied with ui minus ui bar. And this for I going from 0 to n minus 1. And the matrices A, I, and Bi, I gave them these names. They are, of course, the linearization of that system on the trajectory here. So maybe I put it here at the top. AI is defined to be df, dx, dfi at the point xi bar and ui bar. And for Bi, it's the same, it's the derivative with respect to u at the feasible trajectory. Now, and feasible trajectory means it satisfies all these constraints, and that's why these equations simplify a bit. Compared to the usual linear quadratic problem, you get a bit simpler equations. Now, for these linear quadratic terms, I would like to make, so to say, a shortcut to explain them. Yeah. So LQP with index I. Yeah? So what are they? They could be either based on some form of exact Hessian, and then we need, you remember for the exact Hessian, we need the Hessian of the Lagrangian, we need the Lagrange multipliers, and that gets a bit complicated. Needs Lagrange multipliers, and can be indefinite. So there are some problems with that. But this is actually the way that was done in the DDP approach. DDP. And actually, probably that is one of the reasons why DDP itself never really took off, because it was a bit complicated to deal with this indefiniteness. And so the alternative is to use a Gauss-Newton Hessian. I mean, at least if you have a tracking problem, which many cases you have, and many interesting problems can be formulated as for tracking problems. And so this is the approach that actually the SLQ and the also this ILQR approach take. And actually in these cases, we even simplify the things, or to make it really simple, we actually simplify the objective more. So we just say Li of xi and ui is given by nothing else than a quadratic function, which might be penalizing the distance to some reference trajectory, but in the most general form, we can just write it down as something that's like quadratic and having a quadratic and a linear part. So it could be this thing, 1/2, some matrices Qi, Ri, Si, Si, transpose times xi and ui. So that's like the usual thing that we have. And I add some gradient term that I could call, maybe I call it si and qi to be, si and ri to be consistent with, no, qi and si, then it consists of these two letters, right? So these could be the gradient terms that are associated with each of these stages, right? So this quadratic plus a linear part. So, and we assume this thing to be positive definite. So if we have that, and then, and if you're familiar with Gauss-Newton approximations, you remember, okay, after a little bit of changes, I mean, the notation of Gauss-Newton sometimes doesn't really show it, but then, actually, in Gauss-Newton, you will actually have LQPI is the same as the Li. So in Gauss-Newton, we will actually exactly take that objective as the one that we use also in the approximations. And we can do that because we decided to throw away, so to say, the terms that come due to the second derivatives of our system dynamics. Maybe you remember that, but that's like a general feature of Gauss-Newton methods. When you apply it to convex quadratic objectives, you can just basically just keep the objective in the subproblem, and that's what we will do here, which is made easier because we work in both cases in the absolute trajectory space. I mean, these variables x here in the subproblem, I don't use delta x like a difference to the previous trajectory, like you sometimes do in Newton method, but I use the absolute values of the trajectory, not shifted by the reference point. Okay, so then the objectives are absolutely the same, and the same holds for the terminal cost. If the terminal cost was a quadratic, we just leave it. So basically we have these objective terms, these dynamics, and then we can compute a linear quadratic regulator. And maybe I should also mention, I mean, then what is this En of xn is equal to EQP, sorry, it's not En, EQP of xn, and that is given by 1/2 xn transpose p. We can give it the name Pn, I think that's a nice name to give it, and xn. So now we know what the Hessians are, and in the case that we would use the exact Hessian, these expressions for these matrices in the subproblem would be much more complicated, but we would in principle know how to get them once we would know the multiplier. So I will not go into the details yet, but I will just base everything now on this Hessian approximation with these terms here. So I will assume such a form for the objective with this terminal point, and then we are back at linear quadratic, right? So it's just like the general LQR setting. With basically no modification. And now we could write down, and I want to maybe just not write down every equation here, but I want to just give you the general setting of an LQR method. And maybe, I think I wanted to make one change to make it a bit more consistent from the notation. I will give bars to all these quantities which are actually implicitly, possibly depending on the linearization point. So also this thing will get a bar, okay? It's of course a lot of bars now, but this should express these are data that depend on the linearization point. So now, if we would like to solve this problem, this linear quadratic optimal control problem, we would know how to do it with the linear quadratic regulator. So maybe I call this the OCP or the NLP OCP, and this I call the QP OCP. And please note that all these methods, and this is like typical for that method, they work only with unconstrained problems. I mean, you can incorporate constraints in some heuristic forms, but in principle they are not easily extendable. And I will tell you why. So, okay, nothing new until now. We have linearized at a feasible trajectory. We got the subproblem. Now we can compute the step. And now the essence of these DDP-like approaches is that they really say, okay, when we compute the step, we should do it with a Riccati recursion. Well, so we could just say we should exploit sparsity, but actually this Riccati recursion gives us a bit more. So the Riccati recursion gives us not only a solution to that problem, but it also gives us feedback matrices, as you remember, that tell us something about a time-varying linear feedback law that is defined along the trajectory. So, so what we want to do is now we solve this QP OCP with Riccati. And how do we do it? And I will actually maybe sketch a bit what we do is, but we will do one backward recursion for matrices. Yeah. So actually, backward matrix recursion. And you remember how it works. And we did this in principle already, so I will just write the sketch of the formula, but this one just to remind you at the right point. So we will actually get the pi, I mean for I from n minus 1 down to 0, we will get the pi's recursively going backwards. You remember that? So you will always add the stage cost that you got, plus, so to say, a projected stage cost from the time step that follows. Here I have, sorry, this is the pi plus 1. Here is an ai. And then there was this extra term which was very long and complicated, but I will sketch it. And there was a minus 1 in the middle. You might remember that one. And then there was this ri bar plus a term that depended on bi bar pi plus 1 bi bar, and there was a transpose. And here was the cross term that is once transposed and once not transposed, and I should do the transpose at the right side. Maybe I write here transpose, and then I have si bar plus bi bar transpose pi plus 1, and no, sorry, here's an a, right? ai bar. And here's the same. So this same. So that was the recursion, and we start, of course, starting at which value? At Pn defined to be Pn bar. This. Yeah? So we start at the terminal value that we got. Do you remember that recursion? That's somehow what we did. I mean, I didn't derive it yet again, but that's like the most expensive part. Then you have done a backward matrix recursion, but there is something else that you also need to do. And I omitted that detail until now because we never had some terms like this. Yeah? So these extra cost terms here. And I should make sure that I use now the right notation. Qi I have. And Qi bar R I bar. I think I have an error somewhere. This is a pity. But I mean, it's a detailed error, and I will have to correct it in detail. But the big idea is I can transmit already on the blackboard. So what this does is gives us, so to say, the cost to go function, but alone it doesn't give it to us because we have these non-homogeneous terms. If there would be 0, that would be already the cost to go, and would be just a linear function of the initial value at the end. But once we have this, we need to modify it, and we need to move, so to say, these cost terms a little bit with a gradient. Yeah? So what we want to get, and I should say already where this will end, so we will get the LQ cost to go functions. Yeah? So for this linearized problem, and they will look like this. I call that VI of x. And that will be a linear function which gets a constant term which I omit, or which is I'm less interested in it. But then I want to have a pi transpose times x plus a quadratic term, and the quadratic term is what I already computed. So this would be the quadratic expansion that I want to get for my cost to go, yeah, for each of these indices. And okay, the CI is not so interesting. Yeah, so it's just a constant, so it will not impact our feedback law and so on. But this is the gradient that we now still need, and that is that would be 0 if there would be no gradients here. because then it would just, at 0, there would always be the cost 0, but now it's not at 0, the cost 0, and we need to somehow tilt it a bit. And this extra tilting is a backward vector recursion that we need to add, and which we didn't write down in detail yet. I just said at some point, you remember that in principle, you could just augment this whole thing with another state, which is always staying 1, and then you can get it for free, so to say. But, okay, in a real implementation, you would actually need to do some recursion. And so what we do here is we start with, here I forgot one thing. So here we would also need to get a vector at the beginning. So we want to start with a vector also, right? So there must be something more than just quadratic, so it's also having this vector term. And so together with this vector recursion, we will define a Pn that's just starting with this terminal vector. Yeah, then please note that with this definition here, for the matrix and for this vector, we already have the terminal cost perfectly represented. And then we start with a vector recursion that is looking like this equation, and I write it down, and I know that this equation must be slightly wrong, and I will correct it soon. But I think I will not be able to directly correct it now. I'm sorry for that, but basically it will be qi bar. I mean, it contains this gradient here, and then some rotated variants of things that remind you of these terms, but I need to really do it on detail on paper to be sure that I end with the right thing. And what I have here is not exactly the right one. So here's bi bar. Okay, bi bar is 0 in our case. Sorry, I forgot that because, yeah, so I don't need that. Good. So then I have here just pi plus 1. So this is now the small p. And then comes a minus thing, which contains this matrix here again. So I put this, maybe I call this whole thing mi. Here's mi, and here I have mi. Okay, just for matrix something. Here I have this part here. So it's also something we know already. I repeat it. That's like one of the matrices bi bar. And then on the right-hand side, there's some vector term, and that's where I think I still have some error to correct. Ah, no, I just called it si bar. So now I should call it ri bar, then I'm ready, I think. So I know already how to correct it, but I will need to check it in detail. So, yeah, pi plus 1. And here's a transpose. So this would be the vector recursion. So it's also, I mean, it's just the same reasoning that we had for the linear quadratic regulator. But together, these two recursions, they give you the LQ cost to go functions, and afterwards, these are the cost to go functions for this linear quadratic problem. And so, with these functions, we could get also the LQ feedback. So what is now the LQ feedback? It is the one that minimizes the cost to go, one time step in advance, right? So we could derive it again, but maybe I write it down so that we get the spirit of it. So ui star, yeah, so the optimal feedback as a function of the state at that time point is, of course, the argument that minimizes, and now I should be careful, over all u, the system dynamics starting at the point x, and then evaluated at this cost L QP I for x and u, yeah, so that quadratic cost, plus the cost functions that I just wrote down here, vi. I mean, they are for the QP. Should I just give them vi star, so then I'm fine. And I evaluated them at the point a I x plus b I u. You probably remember that, yeah? That was like the control that you get from dynamic programming. That would be the feedback law, and in our case, this could explicitly be computed. And the result will be that it's given by some matrix and a vector ki times x, so it's a linear feedback law, and now I can compute these things, and of course this is again a bit involved, so you see you can take this matrix here, you plug then the A and the B into it, you get a larger matrix, then you optimize for U, you add to this matrix and you optimize for U, and at the end the expressions will hopefully end with this matrix K, which is now minus R bar plus BI, so you see it's always the same, PI plus 1, BI bar to the minus 1, and then here we our matrix BI, this one that I like so much, right? This MI thing, this thing here, and then that's it already, yes. And the vector KI we get from something that is now with a minus sign, the same matrix. And here we have now SI bar plus, and now I should be correct, BI bar transpose times PI plus 1. So you see that implicitly the PI plus 1, which is, oh sorry, here I should have an I plus 1, right? That's important. So I need to look one time step into the future. So the PI, this is the vector, and here's the matrix. They play a role. There's a question.
For the lowercase ki,
yes.
Would that be lowercase ri instead of the si bar in the second?
Yes, sorry, exactly. Yeah, very good point. So that should be the ri. Exactly. That was the writing error that I already. Yeah. So I know now how to correct my things. Thank you. It doesn't appear here, right? Okay. Good. Very good. Thank you. So now we have a way to generate a feedback law, and this feedback law is a linear feedback law, time varying, and in principle we know now that we can get the solution of this quadratic problem by just a forward sweep through our linear systems dynamics with this feedback law, and I will do that first. But now, first another question.
Another stupid question.
No, the first one wasn't stupid. Yeah. So
the first one I did not feel that stupid.
Yeah.
So you compute UI star, which
yes.
is not like a sequence of UIs, it's a single UI, right?
No, actually this is a feedback law. So I didn't specify yet which value x has. So this is actually just a function of x, which at every time step is a different function. So this is like an instruction that says if the state is if the state at time I is at the value x, then this control is the optimal control.
Okay.
Yeah, so it's a feedback law. And once we specify what these values of xi will be, then it's already then I can make values out of it. Yeah, so that's why I keep this dependence on x here. So it's not yet a trajectory or something, it's a control law that's defined at every time point. Like this function is also defined at every time point. So maybe the image we should, I mean, it's like in dynamic programming in general. So this is like time step n, this is time step n minus 1, and so on. And at the last point we have k equals 0 or I equals 0. And these would be the cost to go functions. I called them j at some point, but today I call them vi. Sorry for that. Yeah. Okay, but these are cost to go. By the way, in the literature, both are used. Sometimes people call it v, sometimes j. So it's good to get used to it. But so we have these quadratic cost to go functions, and they all have different curvature and different center points, but they can be generated with these vector recursions. They are related to each other, and once you have them, you can use this control law, which can be solved explicitly because it's a quadratic function of both x and u, and then you get an explicit solution which turns out to be linear in x. So until now there is nothing really new, I think, apart from maybe some hopefully correct formulas. Yes?
I still
yes.
Maybe I
yes.
phrased it wrongly.
Yes.
So like we started out from the problem we have in the top left, right?
Yes.
Where we have the QP OCP problem.
Yes. This is the problem we solve at the moment. Exactly.
My understanding was that like there is a different UI for every time step.
Absolutely. Every time step will have a different UI, right?
Okay.
Yeah.
And so this formula that we now have, the LQ
Yes,
feedback.
yes. So this
If we plug in any xi, it will give you the u.
exactly.
How does it know whether, like, how does it control how does the terminal cost, this EQP,
Yes.
play a role in that? Is that augmented in the value function and that backpropagated?
Sorry, this is the terminal cost, yeah?
Exactly.
And that is entering via the initial condition, namely this one. So you start this vector recursion at this quadratic term. And this second initial condition, namely, for the vector, you also update it with that vector. So that's how the terminal cost enters. But thanks for the question, it really helps, I think. So here is a big P, this is a small p, or capital P, and lowercase p. But these are the initial conditions for the recursion. This is actually, here we have EQP, yeah, so Vn is equal to EQP, right? So this is like trivial, right? And from then on it gets interesting and we get these quadratic terms which are defined by Vi. Yeah, so this would be Vn minus 1 and this would be V0. As a function, I visualize it, so to say, this is a strange plot, but think of this like the state dimension being something going into the blackboard, for example. And then it's a function of the state. But maybe, in principle, I repeat until here only. Yeah, so in principle, you know this idea of forward and then backward. But what we didn't yet discuss is how do we relate that to the nonlinear problem. And so the first and the easiest algorithm is actually what is called SLQ. And that stands for sequential linear quadratic optimal control. Yeah, so that's what it stands for. And what it does is actually exactly as I said, single shooting with a Gauss-Newton Hessian. So how do we get the UIs? Get UI by forward recursion. So we get them by forward recursion. How do we do this forward recursion? We just start at the initial point, initial value. So we get actually U 0 as U0 star of X0 bar bar, right? So the initial point, our initial value. We apply this feedback law to it, and so basically it's K0 plus K0 times X0 bar bar, which is the initial value of our problem anyway. So this gives us the first control. And then, okay, this I should have directly written in general, but then from this you get Xi, X1. How do you get it? You get it by saying, okay, it must be the X1 bar that I had before, because I'm here working with differences only, plus the A0 bar times X, okay, this difference is 0 in this case, so I have nothing to do here, sorry. And then plus my control bar, control dependence is U0 minus U0 bar. Because now this control might be different than the previous control, so I get a slight change in my state trajectory. If there would be no change in this U, there would be also no change in the Xi bar, the linearization point, but because I have it, I will get a change. And then from here on, I go on, and this is why I said I should have written it directly. So I get always like Ui, I get as Ki plus Ki times Xi, right? So this is for I from 1 to n minus 1. And I always get the Xi plus 1 from the Xi plus 1 bar, the linearization point that I had, times Ai times the difference of my Xi and the linearization point, and the Bi bar times Ui minus Ui bar. So this is a linear forward propagation. And that is like what we did always in dynamic programming. That is the way to solve this problem. Yeah? So it's just another way to solve it, and it's so the trajectory U0 up to UN minus 1 solves the QP OCP. I mean, of course, actually also the x trajectory, I should say, yeah, include or maybe together with x. Huh? So these x's would also be together with x0 up to xn. So this trajectory, of course, you can decide to also keep in your problem, but that's not the choice that you do in single shooting. In single shooting, you will just say, okay, now I have got this trajectory, and then the SLQ algorithm is just taking this as this new trajectory. Take, maybe I call this like U star, maybe, yeah. Take U star as new linearization point for next SLQ iteration. So that would be already the SLQ algorithm. Very simple to explain. And there is maybe one caveat that I should say. As I said, it's actually a single shooting method with Gauss-Newton Hessian and Riccati computation of this cost. But you could, of course, also add maybe a line search. But the line search I leave away now because it's getting ugly detailed, so to say. I mean, you can go only partially in this direction and hopefully have decrease in the cost function. And then you need to do some forward and evaluations of your system dynamics and evaluate your nonlinear objective in order to see if you really got progress or not. That's what you would do for a line search. But there was a question.
No, it's
yeah. Okay. Mm-hmm. Okay, so until here, I think we don't have anything really new as an algorithm. Yeah? So it's just maybe good because we repeat it, and we got the framework for the other two algorithms. And I want to, I mean, this one is what I presented first. Now I want to present this one, and maybe at the end I will make some remarks on the third one. Okay, that's like the idea. So this would be subsection 1. So maybe before I continue, are there questions about this algorithm? So how do you see the connection between the nonlinear problem and the linearized problem? And do you see also the point that in principle it's a sequential algorithm because we only iterate in the space of controls? I mean, given a set of controls, you generate, maybe I should also say one thing, because I didn't say it explicitly here, but I said it's a feasible trajectory. And because all constraints are just system dynamics, a feasible trajectory you get easiest by first choosing the U and then simulating your nonlinear system forward by forward recursion, right? That's what we always do. And then at this trajectory, we linearize this whole problem to get this subproblem. But the key of this way of thinking is that we keep it in the full space. I mean, we have the x's here, even though we don't regard them really as variables. Then we solve it with the Riccati recursion, which is efficiently and scales linearly with the length of the horizon and so on. So in particular for very long horizons, this is much better than a condensing-based solution of that thing. We could also condense it. But we don't condense it, we do it with a Riccati recursion. And after we have solved it, we have actually gotten u's and x's. Yeah? The u's are really the thing that we are most interested in. The x's are just a useless byproduct from this perspective because we are not in a simultaneous approach. If you would do that, then you would use the new axis, but with the new axis you would get an infeasible trajectory. So in this approach you just say, I take this U star as a new linearization point, and you actually linearize at a new feasible trajectory. Yeah? Should I write that down? What we get? So get the new, new U bar. Yeah, so the new one. Yeah, so maybe I should call it new U bar plus or something. No, U bar plus from U. I do it a bit similar. What do I do? I could put stars here, but then I mix it with these stars. But yeah, I defined it already here to be U star. So so the new U plus is actually this U star. Yeah? And I get then now my trajectory x plus, yeah, so the new trajectory in the next iteration. Of course, I get it according to this recursion, fi of xi bar plus and ui bar plus. And the starting point is x0 bar plus is equal to x0 bar bar. So the starting point is always the same here. But then I iterate through my system using this control trajectory, and I get my new feasible guess. And you see immediately that this is again a feasible point for the nonlinear problem here. And I then can linearize it again to get this linear quadratic problem and to get the next iteration. Yeah, so that would be the first of our nice algorithms. And now the interesting thing is I would like to keep these things on the blackboard, so I think I better go on for at least 10 minutes. Is that okay? So, despite the heat? Okay, good. So the sequential linear quadratic optimization or optimal control, SLQ as it was called, as I said, doesn't really merit a new name from my perspective because it is single shooting with the Gauss-Newton Hessian and so on. But it comes under this name, and it's also nice to really see how simple it is. And why is it so simple? It is so simple because we didn't have inequalities. Yeah? So there is no need to think about inequalities, so we can just do linear quadratic recursion and so on. And why is it also so simple? Because our Hessians, I mean, when this is a positive semi-definite matrix, and also this Pn, I didn't say it specifically, should be also positive semi-definite, then everything is convex, so the solution of this thing is, I mean, there is no bad local minimum, so to say, or in some mild conditions, it's actually a unique, nice solution. So all these cost-to-go functions, they will also remain convex, and for that reason, these local problems are all well-defined. So it's a really clean algorithm, let's say, with a few pitfalls. But of course restricted to the case that you don't have inequalities. But in practice, people can of course include inequalities by barrier terms. So you could just say, hey, my nonlinear objective here could contain some barrier terms, but okay, now if I have that, I lose of course my tracking property. So I should already say this is not really what you can do with that algorithm. So let's better not discuss in that direction. But what I wanted to do is I wanted to give you now the idea of what the first variation of this algorithm that is already in the DDP type of algorithms, and that is this ILQR method that I want to explain. So actually I think I should put it like 8.9.2, right? So this would be 1 and this is 2. So here's ILQR. So the ILQR method would be not so, why is it called ILQR? Okay, probably it came around the time where iPads and iPods and so on were popular. So that's when people started to use the I in front of things, right? But it stands here for iterative. So iterative linear quadratic regulator. Quadratic regulator. And as I said, it also goes back to some in the first decade of this century, and it's an algorithm that is a slight modification of this whole thing, and I think it's extremely easy to explain. So if you look at this whole setup here, what we do here is we generate our controls and our x's. We need these xi plus 1 in order to generate the next controls, right? Because in order to find the next control, we need the x. But then we throw the x away, and then we simulate our nonlinear system forward here in order to get the next linearization point. So, and this is somehow, it's a bit funny, right? So you first simulate a linear system forward here. Then you throw away the x's, and then you simulate a nonlinear system forward. That's a clean separation, but it's also a bit funny because you could say, hey, if I want to simulate forward anyway, why don't I simulate my nonlinear system forward directly? And this is the idea which makes it a different algorithm. And then from that moment that you use that, what I will explain now, I would call it a new algorithm that is falling into the class of DDP-like algorithms, because this idea was first presented in this 1966 paper. Interestingly, it's an extremely old paper. But it's nearly presented like I will present it, but it looks a bit more complicated because of these Hessian terms and the indefiniteness and so on. But so what does ILQR do? It just gets the new linearization point, U plus. Yeah, so U bar plus is the whole trajectory. Yeah, so I maybe should denote that by a forward sweep through the nonlinear system. So this is the main point, the nonlinear system. So how do we do it? So we start, of course, at x. We also have the new linearization point. So you start with the trajectory, you start there, right? And then you say U I bar plus is given as ki plus big Ki times x I bar plus. This is the crucial difference. So this is not something intermediate, but it is actually really the next linearization point. Or in this case, I go from 0 to n minus 1. And of course, once I have the control, I also get the new xi plus 1 bar plus, because it's the next iterate from the high-level perspective. I apply the nonlinear system, so fi, and I apply it at the current, at the state and at the control that I just computed here. And that is it. So this is a recursion. So what is interesting about this recursion is that when you do the forward simulation of your nonlinear dynamic system, you will incorporate some form of linearized feedback in order to correct not only for, there is a part of this feedback that just comes from, how can I say, from the linear quadratic problem, but there is a little part, because this fi is not equal to its Taylor series, it also already, so to say, gives feedback to the nonlinearity of your system. So roughly speaking, imagine that your aim is to go to some point, so to remain in the neighborhood of something. Yeah? You have your nonlinear system, the first trajectory doesn't go there. You linearize your thing, then it gives you a new control trajectory, but if you would just simulate that control trajectory that we have here, because of linearization errors, it will actually not exactly go, so to say, towards this end point where you wanted it to be, even though the linearized problem predicted that it would go there, but because it's having all these linearization errors, it will still go somewhere else. Yeah, and now this ILQR method or the DDP-like methods, they already correct for that while they do the forward sweep, and that's the crucial difference. Yeah? So the big difference is if you see this line instead of that line. And people in this community, because it's just one line and a very long mixed salad of formulas, right? It's very difficult to spot the difference. But for me, this is the only difference that makes it different from a single shooting method. And so once you have this, I would call it a DDP method. DDP-like. So that's like the main idea, I would say, or the main algorithmic difference of DDP to other Newton-type methods. Okay, and this algorithm is, of course, can also be extended by a line search. And if you want to extend it by a line search, you better write it in a form that is, how do I best imagine it? So if you want to do a line search, you want to have a trajectory, you want to make your steps smaller and make, so to say, a way from having no step to having the full step. And if you do a line search with factor alpha being 1, then it should be exactly this what we have. And if it's with a factor alpha being 0, then it should be the original trajectory that we had before. So now let's make this work. So in order to make for line search, we need to get something doing, and we don't want, I mean, for line search here it's easy. We just, here we would just take the linear combination between the new U and the old U and go partly into it, that's clear. But here we have this extra feedback, and then we go through the nonlinear system, so we need to design this feedback law so that it actually changes nothing if we are with alpha equal to 0. Alpha equals 0, we want to get U bar plus equal to U bar, right? And alpha equal to 1, get the full step, what we had here. So now I need to somehow modify my feedback law to have this property. And it should be linearly depending on alpha. So I start to work on it, and hopefully we end at something reasonable. So the idea is to have Ui plus bar should be equal to the old U that we had before. Somehow that should be Ui bar, all right? And maybe I now modify it so that it's first exactly the same as this formula, and then we add the alpha somewhere, because if we multiply with the alpha and it's 1, then we would still get the same formula. So I need to subtract it at some point, right? So let me do it. So first, I also want to have something that is depending on the difference of ki between kxi plus minus xi bar. So this is the other thing I would like to have. Somehow it should be only depending on differences. So this, you see, this is the old linearization point, and that's a new trajectory. So until now, it's of course not the same that we have here. And so now I need to make it the same by adding and subtracting the same terms, and let's hopefully do it correctly. Hi, so first of all, okay, I make a trial, and if necessary, we make the break, and then I think of it during the break, okay? Good. So first I need to just add and subtract what I just added and subtracted, so I just put it here, so I get a minus Ui bar, and here I need to have a plus Ki xi bar. Yeah? So these are the terms I just added, and then I would just have only that term until now, and then I need to plus a Ki. Plus Ki. Okay. And now, if this would be the formula, it would be identical to that formula, right? So if I set now alpha to 1, if I could multiply any of these things with alpha, and it would get the full step. And now I want it so that if I set alpha to 0, it should just amount to nothing. Changing nothing. And changing nothing could be either achieved by just using this term, because it just means nothing, right? I mean, I don't change. But it could also include even that term. Because if I don't change the first control and the first initial value isn't changed, and this will not change, then the next state will be identical to the previous iteration. So also these differences will be 0. So the trick is to just keep these terms. So now I see that I left too much distance, and just multiply this thing with alpha. So that's the line search that you do. Yeah? So if the alpha is 1, as we constructed it that way, this is 0. And now please note that this whole thing is a constant vector, right? So it's just something that we know before we do the forward sweep. And so these are the vectors that somehow push us into the direction of optimality. Yeah? Constant vector. It's independent of A. That's what I wanted to say, right? It's independent of alpha. So you could do a line search along this line. Yeah? So what you will actually do is, if you realize that after making the full step with this forward recursion, you evaluate your objective, you see that you already didn't improve, then you make the step shorter by reducing alpha, for example, to 1/2. You do the new forward sweep, you evaluate the objective, and hopefully you get a descent. And if you make the alpha small enough, of course this needs to be proven, you get descent in the algorithm. Of course, it's not exactly the same as single shooting, because it gets this extra modification, these things in particular, these feedback terms here, but it's very related. And when you ask practitioners that implemented both these methods, they say they have roughly the same number of iterations. But intuitively, this looks a bit nicer. First of all, you don't have to compute an x trajectory and then throw it away, the linear one. And second, you get somehow already feedback to your nonlinear system errors. So that's a nice feature here. Okay, I think with this, I would have enough material to digest for 10 minutes break, and then we continue afterwards discussing what the original DDP did, which makes it actually a bit more complicated. And the reason for it is that we also need to discuss how we would get to the linear quadratic terms, yeah? Because until now we just assumed for simplicity that the LIs would be given already by a quadratic term. I mean, the linearization and the origin problem are identical for the objective, while in the nonlinear second order method that is of course more generally applicable, we need to somehow think how to get these things. And there's another little smart step in the algorithm that makes it also even more different from single shooting. But it's all small algorithmic details that at least I think I would like to share them with you, because it's also training us of thinking about optimal control algorithms. Are there questions about SLQ and ILQR? Who has ever heard one of these names? Okay. So then maybe I should just say that before going to the workshop in Rome, I attended a PhD defense in Zurich where a robotics person used these algorithms, actually I think the ILQR algorithm, to do very impressive online optimization of walking robots with 4 legs. So these walking robots would just walk with 4 legs and try to optimize their gait given some environment constraints. So it was really impressive to look at that. And it was not only in simulations, but with a real robot that they would push and so on. Yeah. So, and then it was always doing replanning, and because this algorithm is so fast, they did, I think, something like 5 millisecond sweeps. Every 5 milliseconds you would get a new feedback, so you can do nice things with fast algorithms. And so they knew mostly these algorithms, and they didn't know so much about SQP or interior point methods or all this thing that is usually related to direct optimal control methods. But in principle, it's very related, and that's what I would like to make sure that you know, that both these things exist and that you know how to compare them with each other, or how to explain to one person from one community what is happening in the other. Okay, so they are very related. And we do a 10-minute break, and see latest at 30 past, for 25 minutes. Andrea, does it work? Yeah? Okay, good. Okay. 893. Okay, so we continue by concluding this chapter. And now I present you the oldest of the DDP variants, namely the original differential dynamic programming algorithm, which is, as I said, slightly more complicated because of the exact hashing. So this will become section 8.9.3, and it's called DDP with exact hashing. And of course, the benefit of using an exact hashing is that we can directly apply this method to any nonlinear optimal control problem, whatever the objective and cost is. So it's like ILQR. Historically, it's the other way around, but because I like to explain ILQR and it's easier. First, it's like ILQR, but with there's only one difference, so the difference is in the Hessian approximations. So it's with different QI bar, SI bar, SI bar transpose, and RI bar. So these things will be different. And of course, I should also say, and P n bar, which is this matrix at the end, right? So this was the end matrix and this was the end. So how do we get these values? So a linear quadratic approximation of the terminal cost of is quite easy, right? So let's start with the easy part. For the terminal cost, so the terminal linear quadratic cost, what we want is that it's a second order Taylor series, right? So what we want is actually that the function v, how did I call it? I think I called it Vn, right? So sorry, I called it EQP. That's what I said, right? So this EQP should be equal to, first of all, it's something which has a constant and so on. We leave away the quadratic terms, so what it should be actually the linear quadratic expansion of the nonlinear function. So it should be the gradient of this function evaluated at the end point of the trajectory, transpose times x minus xn bar. Xn bar is the linearization point. That's the linear term, so it should be right there. I mean, there's a constant, I leave it away, and then it should also contain the second order term. And this would be, of course, the second order derivative of this function at the point xn bar. X minus xn bar. So this is clear. And now I want to equate that to p. I mean, I put a constant here. Plus something, and these constants we don't care about, so let's just collect linear terms. And now I want to equate it actually to something that is p n bar transpose x plus 1/2 x transpose p n bar x, right? So that's what I said before in order to set up the algorithm. Please note that this is in the absolute values, while here I work with differences. So now let's just look at it. So it's very clear that the only quadratic term in x is actually this thing. So we see already that this will be equal to the second derivative of e at the point xn bar, right? So that's clear. So now what is this value? In order to make these two Taylor series, these two expressions equal, I need to choose, what do I need to choose? Here's a gradient from here, right? There's another gradient from this product of that thing with that point. And that appears twice, because you also get this mix, but it's multiplied with 1/2, and it appears with a minus sign. So what I will get here is it should be the gradient of xn bar, and then minus this Jacobian times xn bar. So it will be this thing, but that's already pn bar, so I can directly write pn bar for it times xn bar. So again, so this is like what the Pn is. So now I know how the first two terms should be determined. Okay, this is actually not so different from what we had before. If that would be a linear quadratic function, it would have been the same. There is no multipliers coming in, so nothing really difficult. This is actually, I think, if you would apply it to a linear quadratic problem, you would get the same expression. Yeah? Same as ILQR. Or SLQ, sorry. So this is not something different. But where it gets really different is for the other Hessian blocks, because these depend also on the dynamics. So please keep in mind what they should be. And they should be equal in the exact Hessian method to something that is actually the second derivative of x and u. Of a function which consists of, it's this Lagrange function, or these parts of the Lagrange function that correspond to the variables of that stage. And this was actually the cost, Li, of x and u, the stage cost, plus the Lagrange multiplier, I plus 1 was its name, transpose times f I xi ui. Do you remember that expression? That's what we had in the exact Hessian methods. Yeah? And of course, sorry, I should not put an I here. And maybe I shouldn't put an lambda here, because I didn't specify it yet. So it should be the second derivative, but of course, at which point should it be? So I should somehow have a bar, and I say here, so to say, x should be evaluated at xi bar, the linearization point of the trajectory. U, of course, at the ui bar, and the lambda at the lambda I plus 1 bar. And yeah, and the second derivative at these points should be what I would like to put into these places. And only then I could get quadratic convergence. Yeah, that's somehow what I need. So this is a bit nasty because in the DDP algorithm I have only u's, right? I mean, the u's are the memory of the system. I can simulate with the u's, I can get the x's. But how do I get the lambdas? So the lambdas are a bit more difficult to get, and there would be different ways of how we could get them. One way that I thought initially would be the most intuitive, but that's not what DDP is actually, would be the one that you just say, okay, I have my u's, I simulate my system forward, I get my x's, xi bars, and then I go reverse sweep with the automatic differentiation basically, and I get the lambdas. You remember there was this equivalence to the lambdas being in the solution of an optimal control problem equivalent to the adjoints. So that would be also a quadratically convergent algorithm, but it's not what DDP does. DDP goes with one less reverse communication, and DDP uses another equivalence which also holds at the solution. And the idea of, so the question is, so to say, how to get lambda bar I. That's the real question. And we need them, because otherwise we cannot compute these hashtags. And so the idea here, use, and now this is like the trick, lambda I bar should be, and this is now the idea, the gradient of the cost function at the trajectory that we just compute as our nominal trajectory. So that's the idea here. The gradient of these cost-to-go functions, which we know because they had these expressions. You remember the expression for the VI, it was this P and the PI squared, right? So if we take the gradient of that, then it's getting the vector PI plus the matrix PI times XI bar. Yeah? And for getting the XI bar, of course, we do a forward simulation. So that was not the difficulty that's like before. But this is the main idea here. So we get our multipliers from this formula, but now it seems like recursive, right? So in order to compute all these matrices Pi and Pi plus these Pi matrices, we need already all the matrices Q, right? In principle. Because that's at least how we implemented it until now. We said we have all this linear quadratic problem, and after we have written it down, the quadratic OCP, we can actually do the backward recursion first in order to get our feedback laws, and then we can do the forward recursion. That's what we did. But now in DDP, because we don't know these multipliers, we actually need to construct even the QP OCP during our backward sweep. So that makes it a bit funny, but it's not a very different algorithm. So the algorithm now goes as follows. So we do a backward sweep like before for the matrix. So here we get a Pi as a function of or something of Pi plus 1. Depends on Pi plus 1. We also get the vector recursion. And there we get this little Pi, which is also a function of the big Pi plus, the small Pi plus 1 and I think the big Pi. So these two things, and maybe also the big Pi plus 1. So somehow it was a formula involving all these things. And then it's interesting. We also, and this is what we had until now. This is nothing new, yeah, as before. But we will also do another vector recursion. Or it's not a vector recursion, it's just a computation, because we get now lambda, after we have these two things, we can get lambda I bar as this expression here, Pi plus Pi times Xi bar. And the beautiful thing is, because we always need, in these matrix recursions, we need always a lambda with the index I plus 1, we already have it at the time where we need to do this matrix recursion. That's the beauty. So starting with what? Starting with, and of course we had here Pn, the matrix was the second derivative of the derivative of the terminal cost. This gradient I said already before was just this, what did I say? It was the nabla E xn bar minus P big N times xn bar. Yeah, so this was our start of the recursion. And where would we start now with the lambda n? So the last multiplier we would get from this formula, which is now, if you look at this, okay, it's like, it's this term plus this term multiplied with xn, but that's exactly that term. Sorry, I should just put this thing here. So, and so this is actually the same as nabla E xn bar. So we have our last Lagrange multiplier, our last P, and if we have all these things, then we can start our recursion to actually compute the Pn, the big matrix Pn minus 1, the vector Pn minus 1, and the lambda we get after we have computed them. I mean, this lambda we get just after we have computed these things, we get the lambdas, and once we have the lambdas, we can evaluate the next of these blocks. But after we have done this first initial step, we know now we can compute big Pn minus 1, little Pn minus 1, and so on, right? So you see that this is a consistent way once we get this definition. That's the new thing in that algorithm. And that allows us to get all the Hessian blocks on the fly, which is, just nice. And some details I should say is, of course, that the Hessian, I mean, in order for this whole Riccati recursion to be well defined, you remember, there is at some point in this formula for the Pi, I just want to give you this thing. If you look at Pi as a function of, it was all these long expressions in this transpose, and then there was a minus 1 and another thing. And this minus 1 was the matrix that we needed to invert, and in this matrix there was this Ri bar plus Bi bar transpose Pi plus 1 Bi bar. So this thing needs to be invertible. If that's not invertible, this algorithm will completely fail, because that was the assumption that we needed to also for this Schur complement lemma to work. You remember how we derived these things? We said this must be a positive definite matrix, because only that way we can actually explicitly solve these stage quadratic problems. So we need to make sure that this is positive definite, and if it isn't, we need to somehow brutally add something to it to make it positive definite. Otherwise, we would get problems. So this needs to be kept positive definite. And it's not necessarily the case, because now we have no guarantee, because this is a second derivative of some nonlinear function. And also this Pi comes from linearizations of some things, and these all these blocks that we have, I mean, already the terminal cost could be non-convex, could be of negative curvature. So then we would have problems at the moment that this thing inherits negative curvature. And if it does, we would just need to add, so if necessary, by force. So what is by force? By force. For example, adding identity matrices. That's like a brutal thing. Yeah, because it destroys all second order derivative information that you had, but it's a necessary step if you want to make this algorithm work. Okay, so that's the first thing, and then the line search is similar, I mean, it's nearly identical, I think, to what we have explained as in ILQR. So there is no difference on the line search there. So that is the original DDP algorithm, and it works actually with the same. I mean, you just need this matrix and this vector recursion, And then after you have done it, you just use this thing to define your lambda I. You can use that to compute this second derivative at the top there, and then you can go on. Yes? Question?
Yeah. First, so for the terminal cost, we have a constant factor that is essentially compensating for the contribution of the x and bar quantities multiplied with the Jacobian and the Hessian, I guess.
So what do you mean? I will just move it down. Yeah.
There is constant plus Hessian of E, x, and bar.
Yeah.
Transpose, and then you have the...
Yeah, so that would be a Taylor series, right? So it's a second order Taylor series, and here's, okay, I should also have plus a constant. And the constants could be different. Thank you for saying that. It's very good. It's
constant on the other
perfect.
side.
Yeah.
So I would compensate.
No. Yeah. No. There must be a constant, and it will be different constants.
Yeah.
They just don't depend on x. That's why I call them constant. So if you would be interested in them, you could compute them. But usually one is not interested in them because we are only interested in the gradients of these things at the end. Yeah. Thank you for asking that question. So that's a true point. Yeah.
The second question that I had was, should there be a transpose the equality of the P and bar?
Which one? Here?
This one, yes.
So there needs no transpose because this metric is symmetric.
No, at the end of the brackets.
Oh, sorry. So, yeah, okay. If you want to have this transpose here, then yeah. If you want to make these two things equal, yeah.
Then there is, I think, on the other blackboard, there is a bar of the y, the lambda m definition starting with p.
Yeah. Exactly.
And
Thank you. I mean, the bars and the non-bars, I think I realize while writing them that it's a bit confusing now because they are not really given before I compute anything, but okay.
Now, a question of understanding, where do the x bar quantities come from during the backwards? Where do we get them from?
Okay. So the backward, they come like before. So before I had just xi bar is just given from the f forward simulation. So I just go with a forward sweep. So they are the ones from my last forward sweep.
Okay,
So the algorithm goes as follows. You first forward simulate with that system. Then you have all your trajectory in x bars, but you don't have the lambdas yet. Then you go backward and you do directly the matrix and vector recursion together with this vector computation of, this is not a recursion, but it's just a computation, right? That way, that will allow you to compute these Hessian terms on the fly, and this way you get the full, second order derivatives into your problem. And maybe I should say that the original way of DDP, how they present it there, is slightly different. I mean, they say, I think they get these Q bar R S, these things. So this is, they are gotten as the second derivative in x and u of a function which is written as the original Li, xu, so the original one, plus, and here they add the vi plus 1 function. This is already the quadratic expansion of fi xi ui. So this is actually even easier to remember, right? So that you don't need to have a Lagrange function and so on. So it mimics as if there would be no Lagrange multipliers. But if you really look at what this means, it is exactly what I wrote down. Yeah, so this is how you could also implement it with Casadi. You could just use the original nonlinear function here, the f also the original nonlinear function, and plug it into the quadratic function that you just computed, and then compute its second derivative. And it turns out that the second derivative will actually just depend on this is not exactly right. So what I wrote down here is plus. I think I need to. I will write it in more detail. So here you would have to subtract the term that you get from the linearization. So it's this is already including, so yeah, this is right if I would just subtract the vi plus 1 ax plus bu. So this term that I have anyway in my dynamic programming recursion. So if I subtract that linear term, then the only remaining term is exactly that thing that we have up there. So I need to figure that out, and please ask me again if I don't write it in time. Yeah? I think we are overdue to finish. I think we will see back on Wednesday. And on Wednesday, I promise to no, I don't. I cannot. I'm on travel tomorrow, so I hope that I will have some this chapter written down in the correct way, so that you can spot errors if you find them, right? And hopefully there won't be any. But afterwards, we will go into continuous time optimal control finally. Okay, I thank you very much, and see you on Wednesday.